Now, if you thought the previous proof was somewhat difficult, you will probably find this one a lot more so. So I'll leave it to you to treat it as a brain teaser. Now, if you're really smart, you may not have any trouble with it. But my feeling is, just based on my experience of teaching this kind of stuff in America to master's students and in China, although it was a mixed class, probably a lot of you will find this difficult. So if you find it too difficult, if you can't get your mind around it, because everybody has a limit of capacity to cope with abstraction. I suppose that's how you define IQ. High IQ people have broader limits, but everyone has limits. Okay, so I'll present the problem. I will show you Sipser's suggested proof solution, and I think I'll leave it to you to figure out why it works. Again, there's a lot between the lines. That's typical of Sipser. Now, if you have an MIT 160 plus IQ, maybe it's obvious to you. If you don't, it's more difficult. All right. Now, what's the problem? So let's see. This will actually be a language, but in the form of a problem. The problem is, can you determine whether you're given a Turing machine? Does it have an equivalent finite automaton? You're just given some random Turing machine. Yes or no? Is there an equivalent finite automaton? Now, two machines, remember, are equivalent if they perform the same job. In other words, they recognize the same language. Okay? Now, we're talking about finite automaton, so that's all it does. That's all it will do. Right? It recognizes a language. It will accept every element, every member of the language, every string in the language. Okay, so that's the problem. Can you, given a random Turing machine, will it have an equivalent finite automaton? Right? Now translate that into a language problem instead of a computational problem. So here's the language title. I'm seriously I should be asleep now. I'm seriously starting to fade. So I sort of think what I will do. I hope my wife quickly gets this new lighting up. So I think I'll start writing up the board around dawn or so, or even a bit earlier. With the new lighting, maybe it won't hurt my eyes. And then I can film during the daylight earlier, and then so I'm less towards the end of my waking hours, put it that way, so my brain is more awake. Okay, so here's the equivalent problem in language form rather than computational problem format. So it's the set of all language, set of all encodings of Turing machines, M. Okay, so M's just Turing machine is the encoding of it, angular brackets, and the language of that machine is a regular language. Now, why why is this computational problem, this language problem, why are they equivalent? Why maybe a good idea to do a bit of revision here. Sipser insists on translating all computational problems into language problems. So let's see, why is that? So if this language can be decided, and that's the whole point, we're trying to show that this cannot be decided, but imagine it can be decided, then that's the problem. Here's a random Turing machine M. Does it have, yes or no, does it have an equivalent finite automaton? Right? So assume there is a machine that can decide this language. Right? So let's say there is here's this random Turing machine. Now this is a set, right? It's an infinite set. All Turing machines that have this language, this L of M, where that L of M is a regular language. So the condition that this is in this language, this set, is that the language of this machine is a regular language. Right? Okay, so imagine we have a decider for this language, and you're given a random machine M. Does it, yes or no, have an equivalent finite automaton? So we use the decider. We input this string into the machine, and it will say yes or no, or rather, it will accept or reject. Okay, so it'll give us an answer to our computational problem. Does this machine M have a finite automaton that's equivalent? Right? So a computational problem can be translated into a language, belonging or not belonging to a language problem. All right. Okay. So the problem statement is that this language is undecidable. Now, proof idea. Now, initially the strategy is much the same as we've done before, so it'll be quite familiar. So I can go through this fairly readily. It's when we come to the key idea, then I think you'll start having problems. So I throw it out not just as a homework problem. It's more like a brain teaser problem. And I suspect this particular proof idea will separate the sheep from the goats, so to speak. The less intelligent will have more trouble, and the really bright should be okay, I guess. Well, interesting to get some feedback. Okay, so the usual thing. So broadly, proof by contradiction, as usual. So we assume then that this language here is decidable, and therefore there's a Turing machine that decides it. We'll call it R, as usual. Okay. And just as before, we'll construct a larger Turing machine called S that uses R, just as we did before. And the job of this larger Turing machine S will be to decide ATM. So we're using the same strategy. All the rationale, the reasoning of the previous session. So we're doing just the same. So I won't go into that again. Okay. So if we can construct this S using R, such that S decides ATM, well, we've got ourselves a contradiction, because we know that ATM is not decidable. Okay. All right. Now, it's not obvious how R, this decider of this language, it's not obvious how this Turing machine R, this decider of this language, how that can help S decide AGM. That is not obvious. Alright, so I'll just throw it at you and see if you can figure it out why it works. Okay? Treat it as a brain teaser. Treat it as a, are you smart enough to figure this out? Okay. Alright, so here's the key idea. So you'll have S has as its input this. So just any old W. Okay. And the M here is the same M as this one. That's important. Okay. And just as we did in the previous problem, we're going to modify M. And you may ask why. Well, so that the proof works. But what I'm asking you to think about, or to try to understand, to comprehend, is the strategy, the underlying thinking. Why was this done? What was the thinking of the guy who invented this this technique? All right. Here's the key idea. Okay. So